Hey, good afternoon, everyone. Apologize for not going today to class. Yeah, but I will be there tomorrow, and I hope you guys are working hard on your project. I will have some visitors that will come to judge the project, hopefully, one at least per lab. I have confirmed one in the morning and another one partially in the afternoon. Let's see. So, quick with respect to the makeup exam, the makeup exam is more conceptual than anything else. It's going to be multiple choice, and it's going to be done in computer. So make sure your access to Canvas is well understood. Otherwise, you're going to waste time there trying to figure out your password. You have to do in the computer that is available in class. Is LE232. So you gotta have your access code. You have to remember your passcode to Canvas. Okay. So that's one thing. The second thing is final exam is going to be more leaning towards the end of the course. There is one subject that I still have to cover, and that is calorimetry. And there is only one equation. I will try to keep as simple as possible, but I need to include that in your final exam because it has to do with heat transfer. But anyways, but basically it's going to be one problem with mechanics that involves energy or the slope or a block going up and down, a problem with pressure, with densities and heights, and I think we did problems on it, and you have that in homework. And Pascal principle, that's important, and um, and uh, and pretty much that's it, I think. So just come prepared, and if you have any question, we can work tomorrow, okay? But these are your midterm number 4. I'm not going to solve step by step, but I will indicate if you can't do by yourself, you can always ask me tomorrow. We have a slope. There is a block that is being pulled up. Oh, by the way, in the final exam, there will be exercise on free body diagram, so you need to know how to do free body diagram, right? And it's being pulled up by a force, external force, 250 Newton. So this block has mass, so we have your mg right here, and this mg projects in mg cosine theta, and several of you forgot this part here, mg sine of theta. And because there is friction, you do have friction too, right? So this friction is equal to the coefficient, which is this number right here, times the normal force. Now, the normal force is balanced out by the gravity projected along the this direction here, which is mg cosine theta. So basically, the kinetic friction is equal to this times mg cosine theta. And then if you take this as your x-axis, your fx net, which is equal to ma. Now you have to populate this part of the equation. So what is fx net? It equals 250 minus mg sine theta minus that coefficient times normal, which is mg cosine theta. And this is equal to ma, right? So with that, we can find acceleration. And I think from there, I think most of you could find a way. If you could find acceleration, you could get the speed, right? You could use coefficient. yeah, blocks at rest, so initial velocity is 0. You want to find the final velocity. We could use Bernoulli and get that done because acceleration was found. Okay. You could use also energy. Some of you attempted energy. So if you do attempt energy, that's part A, and then you go to a part B, A and B. Now, when you do PG, right, at A, which is the lowest part, is 0. B, which is the highest part, would be mgh. But h is the displacement sine of that angle. Okay, I think who tried to do energy got this right, but here was the problem. So if you do take the gravity into consideration, when you do net force, the external work of net force, you include this as net force, you include friction as external force in your net, but you don't include gravity, because gravity is already taken care here. Okay, and then you do your kinetic energy, right? So which is 0 here, and then part B is given by that with our speed we want to find, and then you put the work done by external force, and that would be 250 minus the friction force, which is equal to this times mg cosine theta, right, times the displacement. Sorry, all of that times displacement. This is not applying. Okay. So then you plug this quantity here, and then you can solve for velocity. So half so 200 minus mg cosine theta times d should be equal to half mv final square, and then you can solve for that. Okay. Now this problem here, I don't think anybody, I think one student might have got right. So when you do a free body diagram, for instance, for any of the masses, you have M1 and you have a tension T1 here, right? And for the mass 2, you have also, this is M1G, this is M2G. Now, here's the different thing. Now, the tension now is different. It's not the same because your pulley has mass, okay? And your pulley has a moment of inertia, which is given by some standard equation. So you could use energy conservation, which is the simplest one, and that's how I'm going to do here. But some students attempted to use Newton's law, and if you use Newton's law, you have to calculate the torque here. So with energy is much simpler, and I did that in class. And I said, what if this pulley have mass? So I put it here. So we have a configuration A, have a configuration B. Configuration A, let's say the two blocks are, remember how I did in class, they are at the same distance from the floor. So that would be M1GH plus M2GH. And then after they move a certain distance, right? After they move a certain distance, so if you put them at this distance, so the heavier one goes, which is M1, right? So the heavier one hits this bottom line, and the lighter one, which is M2G, goes up to h. So which means if m1 is the heavier one, it's going to go down h, right? And assume the m2 was there at a height h2. So once this m1 goes down, m2 goes up, right? The same distance h. And as a result, m2 becomes 2h above the floor. Okay. So that solves gravitational potential energy. Okay. Now, how about kinetic energy? That's the tricky part. Kinetic energy, configuration A has none because they are not moving. Start from rest. But in configuration B, there is kinetic energy of both masses, right? Plus the wheel is rotating. And what is the kinetic energy of a rotating body? Half I omega square. And then here on the side, half I omega square is equal half I V over R square, because V over R is omega. Okay, and then you replace moment of inertia by the standard formulation. It does not depend on radius. And then this quantity would be plugged here. Okay, and now we can solve. Now we can solve for V. So we have 1, 2, 3 terms in V square, and everything else is given, and then you can solve. So in this case, I did in class, and I also coach the class what would happen if you have friction, and that's what I put in the exam. So configuration A, configuration B, A you are releasing, B is totally compressed. Major mistakes that some of you did. When you do the potential energy of a spring is half K del X squared. This is the compressional part. So if you have a spring relaxed like this, right, it's totally relaxed. There is nothing attached to it. And the spring has certain length, whatever length that is. And then you compress the spring. So this compression is del X. This is del X, okay? So this quantity is what goes in there, not the length of the spring, and certainly not the length upon which this box has going down. So once you know that, when you do conservation of energy in A, the only thing you have is gravitational potential energy, mg, and then d sine of the angle, right? Sine of theta, the slope. But you have to take also the work done by friction that goes from A to B, and that is equal to the coefficient of kinetic friction times the normal force. I'm not going to do here, but should be mg cosine theta. And that is equal to the energy stored in the spring, half K del X squared. Okay, and then you can solve for the compression part, because K is given. This is the definition of pressure. Pressure is force of area, and then force is equal pressure of area. Just make sure you put the proper units and quantities correctly. Okay, that's one of the exams. Projectile motion. I think we already did this in class several times. If you still have trouble with it, just let me know. There was a misinformation here. 3.5 meters from the base of the cliff, but you can do this is exactly the exam, the question I gave in one of the exams, the same projectile motion question, midterm number 3, I think. So it's there, the solution, and we did in class. For the lacrosse, we want to find the velocity. Velocity is omega r. And the only tricky thing here is 1/4 revolution per second. So V is equal 1/4 each revolution. So you want to get rid of revolution. So we multiply by 2 pi. So each revolution is 2 pi radians, right? And then you have your units correctly. So pi over 2 radians per second. Now, times radius. So the velocity should be pi over 2 times 1.35 meters per second. If you want to know the kinetic energy, half mv squared. And the mass of ball, I kind of gave there. You could put anything. Anything would be fine. 0.20 grams, and then you can solve that. How many times we did this problem in class? And I guess more of you now are doing this correctly. That's great. I don't recommend try to memorize equations for acceleration because each problem is a different situation and circumstances. But basically, you have an acceleration down. You have 63 times g 9.8, and you have a tension T upward. And this pulley, the pulley is there is no information about the pulley, so I'm assuming the pulley is massless. So T minus 63g is equal 63 times acceleration. Acceleration is negative, so it's going to come a negative sign. So T is equal 63g minus 63a. When you look over this block over here, so there is friction. So for the 10 kilograms block, you have kinetic friction. So in X, and I still have a couple of students put in the equation the normal force for F net equal ma. Putting normal force in X, you can't, right? F net is equal T minus kinetic friction, which is coefficient times the normal, ma, then tension minus these times mg is equal ma, and the mass is 10 kilograms. Then basically tension, according to that equation, is coefficient of kinetic friction 10g minus plus, 10a. And now we can solve, g is a known factor, you can solve for acceleration. What we want to find? Yeah, we want to find acceleration, that's how we found. Could use also energy. This problem was funny. I didn't see the development on several students. Several students were just playing with the numbers and getting the final solution, but without showing the steps kind of magically appearing. And I think because of one of the characteristics of the buoyant force is that it does not depend on which material you place it in there. So you can put gold, lead, whatever, the buoyant force is the same as long as the volume is the same, right? It does not depend on the material. So the buoyant force that swimming pool exert on my body is the same buoyant force the swimming pool water exert on a volume of gold that is identical to the volume of my body. The force is the same. So, but how you do that? So we have 30 grams of gold, and we want to know what the scale is going to read. So the scale is going to read the buoyant force divided by g, because scale in this case is reading mass. So what's the definition of a buoyant force? This is important for final exam. It's one of those things you guys have to know. So the buoyant force is equal to the weight of liquid displaced or fluid displaced, which is rho of the liquid times the volume of the liquid displaced times 9.8. Now, for the scale is going to read that divided by 9.8, which is rho of the liquid times the volume of the liquid displaced. But the volume of liquid displaced is equal to the volume of gold, right? The gold is the one that happened to be immersed. So if you want to know what the scale is reading now, right? The scale is going to be reading the 130 grams plus this quantity here, right? That's the addition that goes on the reading. So to figure this out, we need to know the volume of gold. How do we figure that? Well, we have the mass of gold. Mass of gold is given, is 30 grams. But we know that the density of gold was given. That is 9.32 grams per cubic centimeter. That is equal mass times volume. So we can figure here the volume of gold in cubic centimeters. And then you play your cards, either changing to liters or milliliters or whatever. But so you have to take now this volume of gold, plug it in here, and then you can have the reading scale. Okay, and that was this exam. So the other one is this one. So this problem, we want to find the moment of inertia of the wheel. Oops, what happened? We want to find the moment of inertia of the wheel, and is we could use Newton's law, find the torque, but with conservation of energy, as I mentioned in class, that's the easiest you can do. And how do you accomplish that? Configuration A, configuration B, this block is all the way down, and then you use conservation of energy. Implies that in A and B, right, you have these two configurations here. Sorry. So PG. So in A, what we have is MGH, and then block A gets in B. And what else we have? We have that, and pretty much that's it. Assume there is no friction, right? Frictionless. So there are no external forces, and the system is released with a common speed. So let's take care of kinetic energy. Kinetic energy at A is half, right? Mass VA squared, which is 1 meters per second. But you also have to include half moment of inertia of that spinning wheel times omega squared, but omega is the velocity 1 meter per second divided by radius squared. So here we have an equation that I is included, and we want to solve for I. Now in B, what we got, we have this much plus half moment of inertia VB over R squared. Now here's the problem, we don't know VB. So if you know VB, we can plug it in here and solve for I, moment of inertia. So how do we find VB? Well, we use the information given, right? So we have 1 meter per second. So initial velocity is 1 meter per second. The distance covered is 20 meters, and the time is 2 seconds. And then you can find velocity, right? So velocity find a square, velocity is a square plus 2a del x. No, that doesn't work because we have time. How can we do that? So if we have time, we have initial velocity, we have d, we can find acceleration. Okay, so let's do that. Final minus initial is equal v naught t, 1t minus 4.9 times square. Let me see if my signs are correct. So in the initial, this block is going down 1 meter per second, so the speed here has to be negative. So we have to have a negative sign there. Initial is so if you take this as our axis, right? Y-axis. So the initial position is the height. So that would be negative 20 and here 0. So our equation would be 0 minus 20 is equal to negative 1t minus 4.9 pi squared. Why am I doing that? I want to find final velocity. I don't need that, do you? Final velocity VB squared is equal initial velocity. Oh, I'm sorry. I did a silly boo-boo mistake here. Sorry about that. Minus, this is not free fall. What I'm talking about. And then with this equation we can find acceleration. So once we have acceleration, we can plug into the final, which is what we want to find. VB is equal initial minus a times t. And then we can find the velocity, plug it in here, and then we have the problem solved. Certain man has a mass of 80 kilograms. The density is given. Calculate his volume. So the definition of density is mass over volume. And then we can figure his volume. Make sure you plug the proper units. So the mass is 80 kilograms and the volume should be, the density should be in kilograms per cubic meter, and that's the case, so we are good here. So then we find this number. And find the buoyant force the air exert on him. So the density of air that I wrote in the board, 1.2 kilograms per cubic meter. So what is the definition of buoyant force? The buoyant force is the weight of fluid or material displaced, right? The fluid displaced. And in this case is the density of air times volume of air displaced times g. So the density of air was given. Volume of air is the volume of the man that has been calculated previously, times 9.8. 9. This is the same problem as some other preview exam, right? One of these exams. This is the slope. And yes, you have to, I mentioned to the class that you guys should be able to finish this course knowing how to operate these equations and how to show free body diagram and how to determine acceleration. Yes, it's an important, but if you can't do, let me know. Oh, there is something interesting here, and that is you send the block has an initial velocity because this block is going upward, right? But this force is not enough to keep this block moving up. And then what's going to happen is the block's going to have this motion here. It's like throwing something up in the air. Acceleration, if you calculate the number, acceleration here will be negative if you take to the right as a positive direction, your acceleration is negative. So eventually this block stops and then reverse direction, and then you find the value of the speed at this point. Okay. Projectile motion. This is exactly the problem in the quiz all or nothing. The only thing you have to be careful is the angle is below horizon. So your Vy is initial is going to be negative 4.5 meters per second sine, what a bad S, I mean the letter S I'm putting here, sine of 35. That's it. And projectile motion, I'm not going to do it. And those are the three problems, and I try to, I calculate the average of the three exams. They were within 1 point. So I usually, if the averages are too different, then I normalize the exams to the highest average, but it was not necessary. I mean, it was comparable. The level of difficulties were comparable. So what you should do for final exam, which is on Thursday, review pressure, right? Equations that involve pressures. Which equations are those? Well, you have a reservoir, for instance, and you have something over here, right? And this is part A, this is part B. How do you compare pressure part A with pressure with part B? How do you do that? Well, pressure part A is equal to pressure part B plus rho g h. This is h. And rho is the rho of whatever liquid in there. Okay. I can make it more complex if I have, for instance, here's water and here's oil. So if I want to do something water and oil, and I want to say, okay, how pressure A compares with pressure on part C, you cannot say, okay, pressure A is equal pressure C plus, and then you say, oh, but I have density of water and I have density of oil, so what should I do? Should I take an average? No. What you do is, okay, pressure A is equal pressure, not as C, but pressure of B plus rho of water, because that's the liquid in there, G and H. And then you can say, okay, my pressure in B is equal pressure in C plus rho of oil, G times H1, right? And then you can write that pressure A is equal PC, pressure B, right? Plus rho water GH. And now that's how you relate pressure A with pressure C. Pascal principle. So we have these tubes, and we did this in class. It's a classical exam. I mean, if you do an exam to be a teacher or something, or a PG&E or some technical, this Pascal principle will appear, and I can assure you that. So, so we have an area A, you have an area A prime, A2. So, and here you have a big force. You have a tiny, puny force. So, because the pressure at this level is the same in the oil, right? Then you can always say that F over A2 is equal big F over A big area 1. This is always true. So this force divided by this area, which is the pressure here, right, is equal to F divided by A1. This is important too. Don't forget to review your buoyant force. And tomorrow I'm going to mention calorimetry. Calorimetry is how objects exchange heat. And heat, this is energy, right? Energy in joules. Heat is given by the mass of an object times some constant that's called specific heat times the change in temperature these bodies experience. Going along with that is the expansion that we studied before. And then we saw that too, that the length of an object can be expanded if the temperature is changing. So pretty much that's your final exam. Okay? Good luck to you anyways.